All right, so in this video, we're going to talk a little bit about using stoichiometry and balanced chemical reactions and connecting that to calculations with the ideal gas law. And so we know in a balanced equation that it tells us how many moles of the reactants react and what ratio to form the products. And so in this example, we have 1 mole of nitrogen reacts with 3 moles of hydrogen to give 2 moles of ammonia. As an aside, this is a very important reaction, this gas phase reaction. This is called the Haber-Bosch process, probably the most important industrial process, chemical process, because it feeds the world. And so all of our fertilizer comes from ammonia, or most of it. And you're making fertilizer from air. It's really a beautiful thing, from the nitrogen air. Hydrogen, unfortunately, is coming from mostly from steam reforming of methane, which is not a very green process because it's coming from natural gas. So there's carbon emissions associated with that. But in the future, we'll be able to get this hydrogen from splitting water, electrolysis of water, coming from renewably sourced sources of electricity. But really important, this reaction is done at high temperature and high pressure. And this reaction alone is responsible for more than 1% of the world's energy consumption. So that's really an astonishing fact. And if we can figure out how to make this more energy efficient, figure out catalysts for this reaction, you could save a lot of energy. Probably a 3rd Nobel Prize waiting for you if you can do that. There's already been 2 Nobel Prizes awarded for this reaction, this Haber-Bosch reaction, just one in understanding it, and the first one in the early 1900s just for discovering it. But back to using stoichiometry. So we're going to use PV equals nRT here to do some calculations associated with this reaction. And so here's the example problem. If there are 15.0 liters of nitrogen at STP, standard temperature and pressure that stands for, remember, how many liters of hydrogen at 5C and 2 atmospheres are needed to react with all the nitrogen to form ammonia? Okay, so I'm just going to write our balanced equation from before. So that was 1 mole of nitrogen reacts with 3 moles of hydrogen gas. These are all gaseous, by the way, to give 2 moles of ammonia. And what we're going to do here is we're going to first figure out the number of moles of nitrogen, and we want the number of moles of, we want the volume of hydrogen, but what we can do is we can use, once we calculate the number of moles of nitrogen using PV equals nRT and the various other variables we're given, we can use this balanced equation because we know for every 1 mole of nitrogen, we must react with 3 moles of hydrogen. So we can very easily convert from moles of nitrogen to moles of hydrogen. And then after that, we can use PV equals nRT one more time to get to a volume of hydrogen, which is what we're asked for in N. We're asked for liters of hydrogen. All right, so let's start out with PV equals nRT. And we here want to solve for N. We have all the other variables that we need. We have the volume, it's 15. We have the pressure, it's 1 atmosphere at STP. That's the definition of STP. And the temperature is 0 degrees C. That's the definition of STP. 0 degrees C, 1 degree atmosphere. So we'll be able to calculate N because R is always the ideal gas constant. So let's solve for N here. And I'm going to put N nitrogen just to make this clear, because later we're going to be dealing with N hydrogen. So this is the number of moles of nitrogen. We divide both sides by RT, so we get P nitrogen, V nitrogen, divided by R times T nitrogen. Now, I didn't put R nitrogen because, well, the ideal gas constant is always the same, regardless of what gas you're talking about. So at this point, we can start plugging in values. We have 1 atmosphere for the pressure, STP. The volume is 15.0 liters. And then we have the ideal gas constant, which is 0.08206 liters atmospheres per mole Kelvin. Those are our units. And our temperature, well, it's 0 degrees C, but we're going to have to add 273.15 to convert that to Kelvin. Remember, when doing ideal gas law questions, you always have to be in absolute temperature in Kelvin. You plug that into your calculator, get 0.6693 moles of nitrogen. Now, we can use the balanced equation to finish up our roadmap here and keep going, get moles of hydrogen. So 0.6693 moles nitrogen. We know from our balanced equation for every 1 mole of nitrogen, there's an imaginary 1 there, there's no coefficient, but there's imaginary 1 there. We require 3 moles of hydrogen to react with it, because we want to react with all of the nitrogen. We don't want to have any nitrogen left over. So we better have 3 moles of nitrogen there. We multiply that out and we get 2.0 moles of hydrogen. Lastly, now we just need to go N hydrogen, this is N hydrogen, right? Number of moles of hydrogen, to volume of hydrogen. So again, we're going to use PV equals nRT, but this time we know N and we want to solve for liters of hydrogen. So we're going to solve for volume. So volume of hydrogen equals N hydrogen R times T hydrogen divided by P hydrogen. And we just know what N hydrogen is. We just calculated that. That's 2.0 moles. R again is O is our 0.0206 liters atmospheres moles Kelvin. And then we're going to use the temperature. Now the temperature is 5 degrees C. So that's going to be 5 degrees C, again, converting it to 273.15. It's going to end up being 278.15, but just writing it out here so you can see the steps. And then we're going to divide that all by the pressure of hydrogen, which in the problem was given us to be 2 atmospheres. So you add that up to be 278.15, times it by 0.08206, times it by 2, divided by 2, and you get 22.8 liters of hydrogen, and that is your final answer. All right, so it's a long problem. You had to use PV equals nRT twice, and you had to use the stoichiometry of the balanced reaction in order to connect those two PV equals nRTs. Let's do a slightly different one. If there are 15 liters of nitrogen at STP, how many liters of hydrogen now also at STP are needed to react with all the ammonia, all the nitrogen to form ammonia? And this one, again, we still have that same balanced equation. And there's a little bit of a trick on this one because we can save ourselves a lot of time. We could go through and do all the same math, but because this is at STP and it's at STP with the same temperature and the same pressure, we know right away, hey, I have a certain number of moles. I don't know off the top of my head how many number of moles I have, but I know we're at the same conditions. And so whatever volume that is, I have a certain number of moles, I'm going to need 3 times as many, right? Because of I need 3 times as many moles of nitrogen. And since I'm at the same temperature and same pressure, the volume and the moles are just linearly related that way. And so the answer right away is going to be 45.0 liters of hydrogen. And so we can just kind of do that all at the top of my head. Again, just doing 15 times 3. Now, if you're a little skeptical about that and you want to see it done the other way, I'll show it to you in a shorthand way without plugging in a lot of numbers, okay? And so let's solve for N. So we have PV equals nRT. And so last time we solved for N, so we'll do the same thing, N nitrogen. And we'll have P nitrogen, B nitrogen, and R over T nitrogen. And that's fine. So we're going to get some value. Now, what is my N hydrogen going to be? My N hydrogen is just going to be 3 times my N nitrogen, okay? But then I can also write PV equals nRT again, just like we did last time, but now solving for volume. So I have volume hydrogen equals N hydrogen times R over T hydrogen over P. So this time I'm just keeping everything as as variables, not plugging in these S2Ps, just to show you how things are going to cancel out. And so if I do that, I can now do some algebra. So I'm going to sub in 3 times N nitrogen into N hydrogen here. So that will get me 3N nitrogen RT hydrogen divided by P hydrogen, okay? And now I can keep going here. N nitrogen, I know what that is. It equals all this expression, P nitrogen, V nitrogen over R, Tn nitrogen. So I'm going to sub that in. And when I do that, you'll start to see some things will cancel. So I have the 3, then I'm subbing in here for the N nitrogen. So it's P nitrogen. And I got to put my R, T nitrogen. And then I still have this other R up there. I have to carry over in the T hydrogen and the P hydrogen. However, I know that P hydrogen equals P nitrogen, right? They're both equal to the same thing, which is 1 atmosphere in this case. But in general, if the pressures are the same, then we can do some canceling. And same thing with our temperature. Our T hydrogen, and it's both 0 degrees C, which is 273 Kelvin, but those are cancels out. It doesn't matter. 2 hydrogen equals 2 nitrogen. So these are going to cancel out, therefore. These are going to cancel out, therefore. And R's are going to cancel out. So we're left with V hydrogen is just equal to 3 times V nitrogen. So very simply, that's kind of what we intuited, but that's the algebraic proof. So if your temperatures and pressures are the same and you're doing, or any of the 2 variables are the same on either end of this, work through the algebra or work through the logic, and you'll be able to cancel a lot of things out and save yourself some time. Now you could plug in the numbers and it will all work out, and you'll get 45. So, but it could save you some time on an exam or something of that nature.